We're getting started today on circular motion. We have non-uniform circular motion. Uniform circular motion means we were holding a constant speed. Now, today, we're talking about things that could speed up, slow down. So we need to talk about how motion in general works. Tangential displacement was our old displacement from Unit 1, Unit 2, making a reappearance, where we have displacement. What letter was displacement? X. And we put an arrow on top. But for it to be tangential, it just means how is it moving around the outside. Okay, so it's the change in position as it rotates linearly around the circle. Now you're like, but Mr. Kwan, that's a curve. We're just talking about what is it at that instant, the instantaneous motion. What would it emulate? What would it be like? What would it act like? And so that would be its linear motion at that moment. Okay, and it's measured in what units? Meters. Alrighty. Angular displacement comes from our geometry and pre-calc classes, is how we're rotating. And so that's the symbol theta. Theta. And it's measured in radians. Y'all close. Degrees make sense to me too. Radians is how we're going to measure it. And the secret code word that I have for radians is radius lengths, and we'll see that in a sec. Velocity. Velocity is tangential velocity. We've seen this before. It's VT. And these are vectors. VT is the speed of an object. The speed of an object along a line drawn tangent to its circular path, measured in meters per second. So the direction of this velocity is always changing. This is just how we are currently moving at that given moment. We've been given this formula before, that speed is distance over time, right? Did we know that? That VT is distance over time. So it's going to be the X divided by time. And it's the change in displacement over the change in time if it's going to be vector formatted. All right. What is the distance around the circle? If we're going to find it from the average, we could say that we're going around the circle. Distance-wise, how far? 2 pi r. We're going around the circumference in a time period. So that's another way to find it, right? If you have a whole cycle or a whole circle of it, you could find it that way. Angular velocity, however, is going to be given by the letter omega. And it's the rotational speed of an object in a circular motion measured in radians per second. So the direction of this velocity is either clockwise or counterclockwise. And like torque, which way is positive? Yeah, counterclockwise. Alrighty. Omega is equal to, well, it's in radians per second. So what gave us our radians? Other Greek letter. Theta. Divided by time. All of those are vector formatted. And we're going to say that, what kind of units does this have? Radians per second. And so if it has radians per second, if I'm talking about a full circle spin, how many radians are in a full circle? 2 pi over t for the time period. So that's one circle. Now that numerator, 2 pi. That's 2 pi for any circle, huh? So that's a constant. It doesn't matter which way or what circle we're talking about. It's 2 pi per time. If you have the speed that we're rotating around that circle, then it's just 2 pi per time period. Acceleration. Acceleration's an interesting conversation. We've seen acceleration before, but this is not the same acceleration. This is acceleration tangential. Now, to be clear, if I were to show you a circle, we've learned about how something, an object, maybe spinning around there, clings to the center. But this is how something is speeding up. So let's say this is a bicycle wheel. We're looking at AT, not AC, not centripetal acceleration. Centripetal, this is how the bike wheel doesn't fall apart. It spins itself in a circle. The bike wheel is spinning in a circle, and it's glued together with the spokes, the tire rubber, keeps everything intact and from flinging apart in a straight line. AT, however, is if somebody is on a bicycle and they're not moving. And then all of a sudden they decide, hey, look, that light turned green, let's speed up. And so I've gone from 0 revolutions per second to maybe 20 revolutions per second or something like that, or 20 radians per second. That change in speed is the acceleration that we're talking about. The fact that something speeds up is quite literally the definition of this non-uniform circular motion and how we're going to perceive this, that things are changing their speed, or things are speeding up, slowing down in a rotational way, okay? AC was when you held a speed constant, and a lot of times in our problems, when we're talking about centripetal acceleration, I'm not changing my tangential acceleration, or rather I should say I'm not changing my tangential speed. So VT squared over R was that. This, however, is the fact that I'm spinning faster and faster and faster, or spinning slower and slower and slower and stopping and changing directions and spinning the other way. This is going to be AT, how it spins around in a circle, is equal to the change in velocity over time. But our velocity is, nope, I'm getting ahead of myself. It's just V over T. And that's the tangential velocity. And I want to be clear that that is not equal to AC. AC is completely different. Angular acceleration is given alpha. And this is the rotational speed and how it changes in a time period. So alpha, we have over here omega, and the angle was theta. All of those are your rotational quantities. They look a lot like distance, velocity, and acceleration, except they're rotational versions of it. Let's get into problem. Alpha is omega over time. So the question is, what is the formula for alpha? And in the box I have triangle W over T, except that W is a curvy W. It literally means omega. Some of you might have seen the capital version of this, especially if you're in engineering and you've done circuits before. Omega, the capital version in handwriting class, would look like the head and shoulders for ohms of resistance. Alrighty, so if we've got point A, point B, point C, and if we're the observer sitting in the middle, and these are just dots drawn on this disk, how do the rotations per minute of the 3 points compare? They're the same. Good. How do the angular velocities compare? So what about how they spin, how fast they spin around? Well, if I was sitting here looking at them down the line, I would be spinning at the same speed, right? And so they're the same. So what really changes is the tangential velocity that we have. Which one's the fastest? V3 is greater than V2. is greater than V1. Why?
Because it has to cover more distance.
Right.
That is longer than.
So if we're talking about V equals distance over time, 2 pi r over t, then V is directly proportional to the radius, right? If the radius increases, we have traveled more distance in the same time. Alrighty, so that's an easy way to think about that. Well, then there's got to be some relationship between our speed and how we rotate. If we're rotating at different speeds, if we're rotating at the same speed, but we have different tangential velocities, how does that relate? So starting with the definition of tangential velocity, let's assume that point C has just completed one full circle. Well, that means they've all completed one full circle, right? We're going to say that velocity is distance over time, and that's equal to 2 pi r over t. What was the formula for that we said we have for omega? The W-looking thing. 2 pi over t. What's the only difference? There's no radius. So all we would have to do is take and multiply both sides by the radius. So times the radius, times the radius. And then we would see that it's the same. That Vt equals r omega. Right? If you have the radius and you have the radial speed, you just multiply them together to get the linear speed at any given instant. Because you know what proportion you're drawing that circle. Alrighty. So then we've got the velocity versus time equals r omega. But what if we wanted to talk about displacement? And it says multiply both sides by time. This was distance over time. This one was theta over time times r. What happens when we multiply both sides by time? Okay, so our final equation is our position is r theta. This is not new to you, though. If you've taken geometry, do y'all know what formula this is? R theta? It's arc length. It's the proportion of the circle, right? If your whole circle, your theta was 2 pi, then that's how far the circle is, right? R times 2 pi. Well, now we're at some proportion. Maybe it's only like a quarter of a pi. Quarter pi. Well, then it'd be a quarter of a circle times the radius of that circle, and then you get your arc length. So you know that you're even though you've rotated 90 degrees for a quarter pi? No, that's 45 degrees. Even though you've rotated 45 degrees, you would just multiply that times the radius to figure out how far around the arc you've gone. All right. To solve for acceleration, we're going to start in the same place. Vt equals r omega. We're going to divide both sides by the time. So the change in velocity over time and the change in omega over time. What ends up happening? What's velocity divided by time also called? Acceleration is equal to r alpha. Alrighty, so now we have our three bridge equations. We can fill in our chart. We have our displacement versus our angular displacement. And the only difference between the two is multiplying by the radius. This one would be r theta is equal to x. The velocity is equal to r omega. And the acceleration is equal to r alpha. The reverse is true, that if I'm looking for the theta, I could just take the change in arc length divided by the radius. Or if I'm given the speed divided by the radius, that is the rotational speed. And lastly, the acceleration divided by the radius is the Greek version, alpha. Or the spinning version, I should say. The Greek letter alpha. Now, here comes a really quick conversation about what this all means and why we're able to do this all in proportion of its radius length. You should have learned this in elementary school, that the radius length can be stretched around the circle. And you probably know where I'm going with this, that it's stretched around the circle 1, 2, 3, 4, 5, 6, and a little bit, or 6.28. It's because every circle has this pattern going on, that the circumference divided by the diameter is pi. You knew that. It's been a while since we've described it that way, right? But the relationship between any circle's circumference and its diameter is pi. And so when we say this measurement of rotation is in radians, what we're really saying is this rotation of the circle is in proportionate radius lengths. And that's what whispers in my head anytime a pre-cal teacher says radians, is the code word radius lengths. When we do our problems, if you pay attention and we're changing units and you're like, oh, but that's just proportionate to its radius lengths. Anytime somebody says radius or radians, it makes problems seem a little bit easier. So, for instance, if I'm asking you in example 1 to convert the number of degrees in 1 radian, our starting information is that we've got 1 radian. That's what we want the equivalency of. And 1 radian, there's 2 pi radians in 1 circle. And how much is 1 circle in degrees? And so my 1 radius length cancels out with the 2 pi radius length. The radius units goes away, and we're really just doing 360 divided by 2 pi. You type it in the calculator and you get 57-ish. Do I need to pause it? Y'all still doing it?
57.29, right?
Yep. So 57.295 degrees. I just did 3 sig figs because y'all are so used to 3.14 and 360 degrees. Assume the solid disk rotates clockwise in a uniform circular motion. Compare the angular velocity, linear velocity, tangential acceleration, and angular acceleration at points A, B, and C. So they're moving all clockwise. 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 They're all moving clockwise. And we can say that their angular velocity, or if I'm at the center watching them spin, that the angular velocity, what letter is that, by the way? Omega. We said that omega equals, what's a good definition for omega? Earlier we said, yeah, velocity divided by radius would work. As long as we have it in proportion to its radius, that's kind of an interesting concept. But right now, if I'm just trying to define and discuss the three different angular velocities as they rotate, I'm going to say that it's 2 pi over t. Do you remember that from earlier in the notes? It's how we're spinning in a circle. And then we remember that maybe I had pointed out that this is a constant. So in the same time frame, they'll spin just as much. Omega of A equals omega of B equals omega of C in the same time frame. They will spin just as much proportionally to that disk, right? They're all stuck on the disk, and the same disk has an omega, or a rotational speed. And so whatever they're on, that's how they'll rotate. All right, angular velocity. What's the next one? The next one's linear velocity, or VT, tangential velocity. What is included in this one, though? Is it 2 pi over t? I feel like we're missing something. The radius is included. So off to the side, I'm probably going to label that, hey, look. V is directly proportional to R. If I increase the radius, so does the what? Dose. That's my dyslexia kicking in. So does V. If the radius increases, so does V. So the V of C is greater than V of B is greater than V of A. C has the biggest radius. B, and then A is the closest in to the middle. So we have angular velocity, we have linear velocity. What about acceleration values? Bingo. Uniform circular motion. Am I speeding up? Am I slowing down? No? Okay, so the change in omega is 0. So for my angular acceleration, which is alpha, right? Alpha equals W over T. So what's 0? Well, that's 0 over T, right? There is no acceleration. Same logic, delta V is 0. Does it have speed? Yes. Does it have change in speed? No. Okay, let's make that distinguishment right now. Alrighty. So, flip it over to see Mr. Cross riding a bicycle. Board member Cross. I think this was written when he was still a principal here. Maybe we need to update this to Dr. Williams. Board member Cross rides around Cinco Ranch on a bicycle with wheels of 0.3 meters. The wheels make 42 rotations per minute, RPM. Calculate the angular velocity of the wheels. What givens do we have?
Radius.
R is equal to, radius is equal to 0.3 meters. What else did they give us?
We solve for, we get the time frame as well.
We have 42 RPM. Here's the crazy thing. You want to know what RPM is? Rotations per minute. That's a rotational speed. It's a rotational speed, so it says calculate the angular velocity. We already have the angular velocity, but if you look at my answer right now, 42 RPMs, it's not in the units that our answer should be in, radians per second. RPM is the colloquial, the everyday term for rotations per minute is a rotational speed for engines, for disk drives, for a lot of different things. But in physics, we're using radians per second. So how do I take my 42 and convert it? Rotations per 1 minute, right? Can I convert my minutes?
Yes.
How many seconds are in a minute?
60.
So 1 minute up top per 60 seconds, same top and bottom. But my units cancel out. One rotation is how many radians? 6.28-ish. Radius lengths per rotation. So 42 times 2 pi divided by 60 should be about 4.4. I think you get 4.39 or 389 or something. Try it. 4.4 radians per second. What if we're riding the bike for 10 minutes? What's the total angular displacement? How much did the wheels spin? That's what it's asking. How far did the wheels spin? 4.4. We have 4.4 radians per every 1 second. But how far did they spin? We have the radius length. We have the time. 600 seconds. That's what I meant to say. We have the time. 600 seconds. Where did I get 600 seconds from? 10 minutes. 10 minutes. 1 minute per 60 seconds. So 4.4 times 600 is 2640 radius lengths. So now we would only need the size of his wheels and the radius of his wheels to figure out how far he's actually gone. And of course, we don't know how big his wheels are, but if he has like, I don't know, what are big wheels, like 58-inch wheels? Or like, that's a diameter though. Or like the small little trick bicycle wheels, it would make a big difference what this means. Like the BMX? Is that what it is?
It's the type of BMX is the type of bike.
BMX bicycles are the little bicycles that are good for tricks that they do like skateboard tricks type things on. Yeah, is that not in anymore? Used to be so cool back when I was a kid. Okay, never mind. Yeah. Calculate the tangential velocity of a point on the outer edge of one's tires if the wheels does not slip along the ground. What can be assumed about his forward linear velocity? So, we know his rotational speed is 4.4 radians per 1 second. Did they tell us the radius of the bicycle? So 0.3 meters. Meters per what? Meters per radius length. Right? Technically. That's what I was talking about in terms of, hey, if you think about it in terms of radius lengths, you'll start to see that it's just dimensional analysis. Alrighty, so you've got 3 and 4 to get done on your own, and then we'll start new notes tomorrow.